Welcome to GATE Electronic Devices. This is Dr. T. Thirupal, Professor, Electronics and Communication Engineering, G. Pullai College of Engineering and Technology, Kurnool. As we have seen in last classes, and we have been learning about PN junction diode, and we have learned about open circuit PN junction in last class. Now let us go deep into this open circuit PN junction, and let us see the importance of the concepts in GATE examinations and also other competitive examinations. Now, as you see here in today's class, let us learn about the energy band structure, which is present inside of the PN junction. Actually, we have learnt about the structure regarding energy band diagram, where we have drawn in a graph between energy levels and their energy bands which are present in the atomic structure. As we have seen here previously, if you take the energy band of first orbit level is which is very nearer to the atomic this one nucleus, and second orbit, third orbit, likewise we have a valency orbit here where its energy band is EV, and as you go upwards you will have a conduction band energy level EC, and there is a energy level which is lying at center point which is called as Fermi energy level EF, and this gap between EC and EV which is called energy gap which is called EG. So therefore here this is an ordinary semiconductor where it's you can take call it as an intrinsic semiconductor, and if I dope this semiconductor for better conductivity in both p-type and n-type, what is their energy structures actually? What is the shape of that energy structure? Let us see here. Suppose for example this is EC, this is EC, and this is EV, and the Fermi level is lying at center point here for intrinsic semiconductor. If you consider this is p-type semiconductor, that means it is doped with the p-type impurities like boron, aluminum, gallium and indium. Then what happens to this Fermi level? This Fermi level shifts upwards here. It shifts upwards and this one, instead of this one, it is shifting upwards here like this. So this is called a shift in the Fermi level from this point to this point. So I can call this one as EFI, which is a shift in the Fermi level, and this shift in the Fermi level can be written as E1. E1 is the energy level which has been shifted in p-type semiconductor. Similarly, if you take n-type semiconductor, if it is n-type semiconductor, originally the conduction band is here and valency band here. This is EC and this is EV, and the Fermi level is lying at center point in intrinsic semiconductor. Now, if it is doped semiconductor n-type with pentavalent impurities like phosphorus, arsenic, antimony and bismuth, what happens to energy levels here? What happens to energy levels means the energy level EF, it shifts downwards here. It shifts downwards and this will become the Fermi level here. This will become the Fermi level here, which is nothing but intrinsic Fermi level this way. So if you join this two here, the Fermi levels will be here like this. Originally the Fermi level here, this is called shift in the Fermi level, and this shift in Fermi level is given by E2. So here E1 is the shift in Fermi level for p-type semiconductor and E2 is the shift in the Fermi level for n-type semiconductor. Now we need to define what is the shift of this Fermi level in terms of magnitude. So that these are the most important competitive exam questions that will be arising in the GATE examination and also in the competitive exams. So let us see in deep into this energy band structure, where we have a structure like this here. We have drawn here a P region or p-type or n region, n-type region. In between this you have a depletion region or space charge region or transition region. Now I can say here this is the conduction energy band in p-type semiconductor. So that's why I have written here ECP, which is a conduction band energy level in p-type semiconductor, and this is a valence band energy level in p-type semiconductor. This is the original Fermi level where I have drawn in dotted lines original Fermi level. Now here the shift in the Fermi level because of doping with the p-type impurities, so it is shifted here up to this point which is called EFI, and the shift is nothing but E1. Similarly here also you can see here the shift is downwards, EF and EFI, the shift is the energy level which is called E2. So this is the energy gap from this point to this point. Similarly the energy gap from this point to this point is EG, and therefore here As you see, this is a doped semiconductor, so therefore donor energy level will be nearer to Fermi energy level, as we have seen in structure of an atom or atomic structure. So here the shift from original EC to the shifting level is nothing but E naught. E naught is nothing but it is the energy level which is been given to the charge carriers, and this been shifted from this point to this point. The same level it's been shifting from this point to this point because it's an acceptor energy level which is nearer to Fermi level. So this is nothing but E naught, and this E naught can be also be represented in terms of gap like this. Here this is a gap from this point to this point. This is represented by E naught. E naught. So where E naught, I can write it as E1 plus E2. E naught can be written as, it is the potential energy barrier for electrons. I can say that E naught is the potential energy barrier for electrons, and also it can also be represented for holes. So I can represent and talk it as potential energy barrier for charge carriers. So E naught is equal to, can be written as E1 plus E2, or you can write this one as energy gap Eg can also be written as EC minus EV. EC minus EV. You can take it as a p-type semiconductor, or you can take this one as an n-type semiconductor. So the energy gap Eg is equal to EC minus EV. And we have a shift in Fermi level here. We can write this one as shift in Fermi level in p-type is EFI minus EF. And the shift in Fermi level here, it is written as EF minus EFI. So these are the most important cases. Now let us have the equations for E naught, Eg, and the shift in Fermi levels in p-type and also in n-type semiconductors. Okay, the first one. For suppose we have already learnt in semiconductor physics that concentration of holes and concentration of electrons. Concentration of holes is given by P is equal to NV, which is effective mass of holes, into e power minus of EF minus EV divided by KT. That is, concentration of holes is given by P is equal to NV into e power minus of EF minus EV divided by KT. Similarly, we can write this one as for concentration of electrons as N is equal to NC. NC is called effective mass of electrons in conduction band. This is effective mass of holes in valence band. N is equal to NC into e power minus of EC minus EF divided by KT. As we know that according to mass action law, N into P is equal to Ni square. So N into P is equal to Ni square. N is nothing but NC into e power minus of EC minus EF divided by KT into NV into e power minus of EF minus EV divided by KT is equal to Ni square. So therefore, it is equal to NC into NV into e power minus of EC plus EF minus EF plus EV divided by KT. So therefore, here EF gets cancelled. That is equal to Ni square. So NC into NV into e power minus of, take out minus common, EC minus EV divided by KT, that is equal to Ni square. So therefore, NC into NV divided by Ni square is equal to e power minus comes like this, e power, it will become plus e power ec minus ev divided by kt. So apply natural logarithm, you get ec minus ev is equal to, apply natural logarithm and multiply with kt, so you get kt ln nc nv divided by ni square, nc nv divided by ni square. This is called ec minus ev, which is also nothing but ec minus ev is called eg. So this is called energy gap. Energy gap is equal to ec minus ev divided by ec minus ev, that is equal to kt ln nc nv divided by ni square, where nc is called effective mass of electrons in conduction band, nv is called effective mass of holes in valence band, ni is called intrinsic concentration, and kt, you know already, kt by q is a volt equivalent temperature. So this is called energy gap Eg, which is equal to kt ln nc nv by ni square. Next, let us have the equation for E naught in terms of Eg. So as you see in this diagram, as from the diagram, we know that from the diagram, E naught is equal to Eg minus of, it is equal to Eg minus of Ec minus Ev. That means you can see here, which is nothing but E naught is equal to the whole thing, which is Eg minus of Ec and minus of Ev. This is called Ev. So Ec minus of Ev, I can write as Ec minus of Ev, or else we can write this one as like this. E naught is equal to Eg minus of Ec can be written as Ecn minus Ev can be written as Evp. As you see like this, Ec is nothing but Ecn, and this level is called Evp at this level. So if you want to find this level, you need to subtract Ecn and Evp from Eg. So therefore, I got an expression E naught is equal to Eg minus of Ecn minus Evp. So that is can be written as E naught is equal to Eg minus of Ecn minus it is equal to Ef minus of, it can also be written as minus of, it can also be written as Ecn minus Ef, and also it can be written as Ef minus Evp, Ef minus Evp, Ef minus Evp. So if you do it, minus Ecn minus of minus is plus, and minus Ef gets cancelled, so we can write this one as Ecn minus Ef and minus Ef minus Evp likewise, right? Now let us see what is this Ecn minus Ef and Ef minus Evp. So already we have Eg equation we have already, and what is this Ecn minus Ef and Ef minus Evp? So we have here, as we know that n is equal to nc into e power minus of Ec minus Ef divided by kt. So if it is n-type semiconductor, I can write this one as n is equal to nd, donor concentration, that is equal to nc e power minus of n-type semiconductor, it is Ecn minus Ef divided by kt. So therefore, from this I get Ecn minus Ef is equal to kt ln nc divided by nd, kt ln nc divided by nd. Similarly, for p-type semiconductor, p is equal to nv into e power minus of Ef minus Ev divided by kt. So p is an acceptor concentration for p-type semiconductor, so I can write this one as Na, that is equal to nv into e power minus of Ef minus Evp, because it's a p-type semiconductor, divided by kt. So therefore, I can get from this equation as Ef minus Evp is equal to kt ln NV divided by NA. So this is one equation I got. This is another equation I got. Substitute all these equations including EG also. From this we got from the last equation EG also we got. So we got E naught is equal to EG. What is EG? EG is equal to KTLN NC NV divided by Ni square minus of ECN minus CF. From that equation we got KT ln NC by ND minus KT ln NV divided by NA. So therefore I got E naught is equal to KT ln NC NV divided by Ni square whole divided by, since it is minus, so you get NC by ND into NV by NA. So NV, NC gets cancelled. So the remaining equation is E naught is equal to KT ln NA ND divided by Ni square. E naught is equal to KT ln NA ND by Ni square, where Na is called acceptor concentration, Nd is called donor concentration, and Ni is called intrinsic concentration, and K is Boltzmann constant, T is the temperature, E naught is the energy level, potential energy barrier or energy level for charge carriers in order to move from P type to N type or from N type to P type. So from this we can able to find the potential energy barrier for holes also. This is the potential energy barrier for electrons. So now the potential energy barrier for holes is given by V naught. V naught is equal to, we have a formula in terms of E naught divided by E. E naught divided by E. So V naught is equal to E naught divided by E. If you substitute E naught here, you get KT by E into ln Na Nd divided by Ni square. So therefore, as KT by E or KT by Q, which is nothing but a charge of a carrier, we know that it's nothing but volt equivalent temperature. So therefore, V naught is equal to Vt ln Na Nd divided by Ni square. So this is what the equation we got, potential energy barrier for holes. In order to make sure that hole has to move from P type to N type, it has to overcome that potential energy barrier. But what is that potential energy barrier means? This is the amount of potential energy barrier in terms of magnitude, where V naught is equal to Vt ln Na Nd by Ni square, and this is the potential energy barrier for electrons, which is E naught is equal to KT ln Na Nd by Ni square. Now similarly, the same expressions can be updated, enhanced to P type and N type semiconductor using mass action law. So according to mass action law, we know that N into P is equal to Ni square. N into P is equal to Ni square. For P type semiconductor, we know that Np suffix Pp is equal to Ni square. As you know already, Np is nothing but minority charge carrier present in P type, and Pp is nothing but acceptor concentration Na in P type, that is equal to Ni square, which is a majority charge carrier. Na is called majority charge carrier. So I can write this one as Na is equal to Ni square divided by Np, or you can write this one like this. Similarly, for N-type semiconductor, we have Nn into Pn is equal to Ni square, where Nn is the majority charge carrier. So I can write this one as donor concentration into Pn, that is equal to Ni square. So therefore, Nd is equal to Ni square divided by Pn. Right. Now the previous equation, from the previous equation for potential energy barrier for holes, V naught is equal to, we have Vt ln Na Nd divided by Ni square. So from this we have got V naught is equal to Vt ln. Since Na is written here, Na is equal to Ni square by Np. Ni square, I am writing Ni square by Np into the remaining thing Ni square. Ni square gets cancelled. So therefore, V naught can be written as Vt ln Nd, donor concentration. Donor concentration is nothing but in N type electrons, Nn. So it can be written as Nn and divided by denominator is Np. So another formula exists in atomic this one structure of element here. V0 is equal to Vt Ln Nn by Np, where it represents Nn represents majority charge carriers in N type and Np represents minority charge carriers in P type semiconductor. That means both are relating to electrons here. So the same equation can also be written in terms of minority charge carriers. I can write this one as V0 is equal to Vt Ln Nn naught divided by Np naught, where it can be written as like this, where Nn naught is at room temperature. Nn naught represents minority charge carriers at room temperature. Here minority charge carriers at room temperature. So I can represent this one as Nn naught divided by Np naught. Similarly, I can also be representing the same equation like this. V naught is equal to, as I have V naught is equal to Vt Ln Na Nd divided by Ni square. It can also be represented as V naught is equal to Vt Ln. Instead of Nd, I can write it as Ni square by Ni square divided by Pn. And already I have Ni square gets cancelled. So I have V naught is equal to Vt Ln Na divided by Pn, and Na is acceptor concentration. I can write V naught is equal to Vt Ln. Acceptor concentration is holes, so I can write this one as Pp divided by Pn. That means it is talking regarding a holes concentration, holes in P type and holes in N type concentration. Right. This is another formula where we can obtain the potential energy barrier for holes, that is V naught is equal to Vt Ln Pp naught at room temperature and Pn naught at room temperature. N naught represents at room temperature, at thermal equilibrium position, means at room temperature. What is the potential energy barrier for holes? So V naught is equal to Vt Ln Pp naught by Pn naught. Similarly, V naught is equal to Vt Ln Nn naught by Np naught. So these are the most important equations that comes under competitive exams, where you need to remember it properly, right? So these are the famous equations. Next we will go for another equation where the shift in Fermi level is been obtained, because most probably questions have been asked in a shift in Fermi levels. So let us have the shift in Fermi levels here. What is the shift in Fermi level? Shift in Fermi levels. Shift in Fermi levels, right? Now see, we have whole concentration as P is equal to Nv e power minus of Ef minus Ev divided by kT. And also we have N is equal to Nc into e power minus of Ec minus Ef divided by kT. So from this, as we know that N is equal to P is equal to Ni for intrinsic concentration. N is equal to P is equal to Ni for intrinsic semiconductor, because number of holes is equal to number of electrons in intrinsic semiconductor. So I can write this one as Ni is equal to Nv into e power minus of EFI, intrinsic Fermi level, EFI minus EV divided by kT. Similarly, here Ni is also equal to Nc into e power minus of Ec minus EFI divided by kT. It's an intrinsic Fermi level. It's an intrinsic Fermi level. It's an intrinsic Fermi level. So I have intrinsic Fermi level as Ni and this one as Ni. Now let us go with the shift in Fermi levels. What is that shift in Fermi level? From this equation, we have P is equal to NV into e power minus of EF minus EV. Now, what I am doing is, for this equation, I am adding and subtracting EFI, energy for intrinsic energy Fermi level, as EF minus EFI plus EFI divided by KT. Now, I am dividing into two parts. P is equal to NV into e power minus of, this one can be written as NV into e power minus of, I can write this one as EFI split into two parts, EFI minus EV divided by KT into e power. I am splitting into two parts. One, I am taking this EFI and I am taking this EV, EFI minus EV. Next, the next one is e power minus of, what are the remaining terms? So the remaining terms are minus of EF minus EFI. These are the remaining terms, EF and EFI. So EF minus EFI divided by KT. So now P is equal to, instead of all this, I can write as intrinsic concentration Ni. So therefore P is equal to Ni into e power minus of EF minus EFI divided by KT. So from this, bring this one this side and bring this P this side. What you get is EF minus EFI. EF minus EFI is equal to KT ln Ni divided by P. Where shift in the Fermi level in P-type semiconductor is EF minus EFI is equal to KT ln Ni divided by P. This is please do remember this important equation. Shift in the Fermi level is EF minus EFI is equal to KT ln Ni by P. Okay, or else the another formula you can have EFI minus EF is equal to KT ln P divided by Ni. You can also have this equation provided that you have EFI minus EF. Okay, right. Next, similarly, what is the shift in the Fermi level for a n-type semiconductor? So from this equation, I have N is equal to Nc into e power minus of Ec minus Ef. I am adding and subtracting both the terms, EFI minus EFI divided by KT. So I got here N is equal to Nc into e power minus of, I am bringing two terms as Ec and minus EFI to one side divided by KT. The other thing is e power minus of remaining terms. This one I have shifted and this one I have shifted. The remaining terms are minus of EFI minus EF divided by KT. So therefore N is equal to, instead of this one I can write this one as Ni into e power minus of EFI minus EF divided by KT. So therefore from this equation I got from this equation as EFI minus EF is equal to KT ln Ni divided by N, which is a shift in Fermi level in n-type semiconductor. EFI minus EF is equal to KT ln Ni divided by N, or EF minus EFI is equal to KT ln N divided by Ni. N divided by Ni. So these are the most important expressions where the shift in the Fermi level happened in P type and also happened in N type semiconductor. So if you want to find those shift in the Fermi levels, you can have these expressions. Okay. Now let us go through some important questions that has been asked in the previous examinations. First one, the following is the band diagram of a junction between two semiconductors A and B. If both A and B are silicon, the doping in A and B are respectively dash and dash. So this is A is given here and B is given here. That is one type of semiconductor, this is one type of semiconductor. But he has given here the conduction energy band is nearer to Fermi level here. But here this side Fermi level is lying at center of EC and EV. So as we have already told that Fermi level lies at center of EC and EV, conduction energy band and valence energy band. When it lies in which type of semiconductor? It lies especially in intrinsic semiconductor. This is nothing but intrinsic semiconductor, right? Now here, as conduction energy band is nearer to Fermi energy level, so what happens? What are the dopants that is been added so that the conduction energy band is nearer to Fermi energy level? If you add N-type dopants, if you add donor impurities, if you add p-type impurities, if you add pentavalent impurities, then conduction energy band is nearer to Fermi energy level. So now, and as you know that valence energy band is farther away from Fermi level, so therefore this is what type of semiconductor? It is N-type semiconductor. So therefore the option here is D, which is N and intrinsic semiconductor. That is N and this is intrinsic semiconductor, right? So likewise you need to solve the problems. Next, a small percentage of impurity is added to an intrinsic semiconductor at 300 degree Kelvin at room temperature. Which one of the following statement is true for the energy band diagram shown in the figure below? This is the energy band diagram where it is shown. And here 0.01 electron volts is given here. That means this is nothing but donor energy level. This is called donor energy level. Donor energy level is very nearer to EC. So therefore, what type of dopants are there here? What type of impurities have been added here? Definitely it is an N-type semiconductor, which is nothing but a pentavalent impurities are added here, right? So therefore now see the option for intrinsic semiconductor, which has been doped with what type of pentavalent atoms to form N-type semiconductor, right? That is the correct option. Let us say other options also. It is intrinsic semiconductor doped with trivalent atoms to form N-type. This is especially wrong because only pentavalent atoms it will form N-type semiconductor, not trivalent atoms. Trivalent atoms if you add it will form P-type semiconductor, right? Next, intrinsic semiconductor doped with pentavalent atoms to form P-type. This is reverse, vice versa. Pentavalent atoms it will form N-type semiconductor, not P-type. Intrinsic semiconductor doped with trivalent atoms to form P-type semiconductor. This statement is correct, but it is not suited to this figure. If it is suited to this figure, this level should be here. It should be nearer to valence energy level. But here in the problem, it is given donor energy level, it is nearer to electron. So therefore, I can say that this sentence is correct, but it is not suited to this figure. So which sentence is suited to this figure means option A is suited to this figure, which is intrinsic semiconductor doped with pentavalent atoms to form N-type semiconductor, right? Next. Silicon is doped with boron to a concentration of 4 into 10 power 7. So boron means what? It's a P-type. P-type means P-type semiconductor. So P-type concentration is given P is equal to 4 into 10 power 7 atoms per centimeter cube. Assume the intrinsic carrier concentration of silicon. Intrinsic carrier concentration is given Ni is equal to 1.5 into 10 power 10 per centimeter cube. And the value of Kt by Q to be 25 millivolts. Vt is given 25 millivolts at room temperature. Compared to undoped silicon, the Fermi level of doped silicon is. What happens to Fermi level of doped silicon? Because here what type of doping you are adding? P-type dopants you are adding. So if you add P-type dopants, then what is the formula here? Just now we have seen the P-type dopants. EF Fermi level in P-type. So this is intrinsic Fermi level, right? So EFI minus EF is equal to KT ln Ni divided by P. KT ln Ni divided by P. This is the equation what we have already seen in last class. EFI minus EF. EFI minus EF is equal to KT ln P by Ni. It is P by Ni. KT ln P by Ni. So therefore EFI minus EF is equal to KT ln P. P means 4 into 10 power 7 divided by Ni 1.5 into 10 power 10. So if you do it and if you apply here, KT is KT by Q, we have 25 millivolts, but here you can write this one as 25, given it is 25, it is milli electron volts, because Q is not given, only KT is given, right? So I can write KT as 25 milli electron volts, ln of this one. So therefore I get, if you do all this, you get an answer as 0.427 electron volts. So that is EFI minus EF is equal to 0.427 electron volts. So what is this intrinsic? It is doped semiconductor. It is the original one, EF. So therefore compared to undoped silicon, the Fermi level of doped silicon is, what is the Fermi level of doped silicon? Fermi level of doped silicon, what happens is, Fermi level of doped silicon, EFI minus 0.427 electron volts is equal to EF. So Fermi level of doped silicon is decremented by this one. So therefore it is going down by 0.427 electron volts. It is going down by 0.427 electron volts, because it is subtracted here, it is been going down here. Okay, so that is EF is equal to EF5 minus 0.427 electron volts. Next, an n-type semiconductor having uniform doping is biased with V volts. If EC is lowest energy level of conduction band, EV is the highest energy level of valency band, and EF is the Fermi level, then which one of the following represents the energy band diagram for the biased n-type semiconductor? Let us see for biased n-type semiconductor. See the first option A, EC, EF. EF is very near to EC, so therefore, and EV is here. But if this one is, if this is P-type and this is N-type, right? This side is P-type and this side is N-type. So which one is the biased one for N-type semiconductor, right? Now here both are, Fermi level is nearer to EC, here also nearer to EC. So therefore this is not the right answer, because P-type, as you know, that Fermi level shifts for P-type and also N-type, and especially it's been asked here for N-type semiconductor. So let us see what is the correct answer for N-type semiconductor. Next, here also see. So this is EC, which is a constant here. This is also not shifting, and EF is shifted here, but EC is here itself. But EC energy level also has to shift, because it is a doped one. So therefore this is also not right answer. Next, here, since it has been asked here only N-type semiconductor, but here P-type it has been shifting, EC is shifting and EF is shifting towards P-type. So therefore this is right. So now EC is shifted here, EF is shifted. So because it is doped with N-type semiconductor, so this is the right answer. So D is the right answer, right? Okay. So we'll stop over here. Thank you so much for listening to the class. Thank you.